Imagine you are teaching a student to play the piano. They spend months mastering a difficult piece of music. Then, you hand them a violin and ask them to learn a new song. If you do not manage the transition carefully, the student might forget the piano piece entirely. This is a fundamental challenge in artificial intelligence known as catastrophic forgetting. When machine learning models are deployed in the real world, they often face a stream of new data that arrives continuously. They must learn this new information without overwriting what they have already learned. If the model forgets the old data, it becomes unreliable for long-term use. This problem is particularly acute in continuous deployment environments where software updates are frequent. Traditional neural networks rely on static synaptic weights. Think of these weights as fixed connections between neurons that do not change once training is complete. In a static environment, this works fine. But in a dynamic environment where the world changes, static connections are insufficient. The system needs a way to adapt without losing its core knowledge. This is where the concept of intrinsic stabilization of synaptic plasticity becomes crucial. It is not just a theoretical idea from biology. It is a practical architectural blueprint for building robust artificial intelligence systems. To understand how we can solve this, we must look at how the human brain handles the same problem. Our brains are constantly learning new things throughout our lives. We do not forget how to speak our native language just because we learned a new one. This resilience comes from mechanisms called homeostatic plasticity. In biological terms, this means the brain actively regulates its own activity levels. When a neuron becomes too active, it dampens its own response. When it becomes too quiet, it strengthens its connections. This balance ensures that the network remains stable even as it learns new patterns. In the field of artificial intelligence, researchers are now trying to replicate this behavior within the code itself. The current consensus suggests that we cannot rely on simple pairwise interactions between neurons. Pairwise interactions mean looking at only 2 points at a time to decide if a connection should strengthen or weaken. This approach is too limited for complex environments. Instead, we need to look at group-level spike synchrony. This means observing how groups of neurons fire together in time. By leveraging this synchrony, we can drive the network toward an equilibrium state automatically. This is the core of the plasticity-driven learning framework. It allows the system to learn the rules of plasticity itself rather than having those rules hard-coded by a human engineer. Another critical insight comes from the concept of three-factor learning. In traditional models, learning is often driven by just two factors, the activity of the presynaptic neuron and the postsynaptic neuron. However, biological systems often use a third factor, such as a modulatory signal that acts like a dopamine reward. This signal tells the network whether the current learning event is important or not. By incorporating this third factor into our architectures, we can prioritize which memories to keep and which to discard. This creates a more nuanced approach to memory management. It allows the system to distinguish between noise and significant new information. Now consider how we translate this into a production machine learning pipeline. We are not just talking about training models in a lab. We are talking about embedding intrinsic stabilization layers directly into the deployment infrastructure. These layers act as a monitoring system that runs alongside the main model. As new data arrives, these layers detect signs of instability. They look for indicators that the model is beginning to forget previous tasks. When such signs appear, the stabilization mechanism kicks in. It adjusts the internal parameters of the network dynamically. This might involve changing the plasticity thresholds or scaling the learning rate for specific connections. The goal is to maintain a state where the network is always ready to learn, but never at risk of losing its foundational knowledge. This approach also has significant implications for energy efficiency. Traditional deep learning models often require massive amounts of compute power to retrain or fine-tune. By using biologically inspired learning frameworks that infer neural activity prior to synaptic updates, we can reduce the computational overhead. This is particularly relevant for neuromorphic hardware, which is designed to mimic the physical structure of the brain. When intrinsic stabilization algorithms are integrated with these chips, the system can learn continuously with minimal energy consumption. This opens the door for AI systems that can operate in real-world settings for years without needing a complete retrain. There is a notable gap in the current literature regarding the precise definition of intrinsic stabilization as a unified mechanism. Different studies use different terms. Some focus on optimizing intrinsic neuronal parameters. Others focus on complexity-based encoding. While they all agree that moving beyond static weights improves adaptability, the field lacks a standardized theoretical framework. This means that engineers building production systems often have to choose between different approaches without a clear guide. Future work must bridge these distinct approaches. We need to establish a cohesive understanding of how internal stability mechanisms facilitate superior learning across different architectures. Until then, the blueprint for embedding these layers remains the most practical path forward for anyone serious about continuous learning. Implementing complexity-based encoding allows artificial networks to dynamically adjust their plasticity thresholds. This leads to superior performance in continuous control tasks. It means that a robot arm, for example, can learn a new grasping technique without losing the ability to perform the old one. It also means that a recommendation engine can adapt to changing user preferences without suddenly suggesting items the user has already shown interest in. The integration of these principles suggests a future where AI systems are not just static tools, but living systems that evolve with their environment. The path to this future requires a shift in how we design our systems. We must stop viewing neural networks as static functions that are trained once and deployed forever. Instead, we must view them as dynamic systems that require ongoing regulation. This involves writing code that manages the health of the network itself, not just the output. It involves building pipelines that can detect drift and apply stabilization rules automatically. It requires a deep understanding of both the mathematical underpinnings of plasticity and the practical constraints of production environments. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.